Do you have a favorite bird species? I hate to play favorites, but I'll say that I find cranes, especially sandhill cranes, completely fascinating. In one of the world's most amazing wildlife migrations, tens of thousands of sandhill cranes fly from the Gulf of Mexico and other southern wintering grounds north to the Platte River in Nebraska. Cranes are among the world's oldest bird lineages, having been around since the end of the Eocene 34 million years ago. Some of the world's cranes are now endangered due to pollution and habitat change, while sandhill cranes remain the most common of all the cranes since rebounding from near extinction in the 1930s. In November 2014, in fact, a flock of 24 cranes was observed flying south from their nesting site in southern Maine and down the Atlantic seaboard, the largest recorded flock on the Atlantic flyway in 2 centuries. According to the fossil record, sandhill cranes and their ancestors have been undertaking this long-distance migration for millions of years. During the ice ages, livable habitats were restricted, and as the ice receded, the cranes would fly farther and farther to follow winter's warming edge, arriving in America's sandhill regions as the spring began. Today in the spring, over 250,000 sandhill cranes may be seen along an 80-mile stretch of the Platte River, where they fatten up alongside millions of migrating ducks, geese, and other birds in the almost barren cornfields before their trip farther north to nesting grounds in the boreal forest and subarctic. Cranes are highly social birds that react to one another's body posture and vocal cues. So when several lift off, many also take flight. Ornithologists have found that the cranes on the Platte may even fly to the same sandbar each year. These areas have vast quantities of invertebrates, fish, frogs, and even snakes that the cranes and their offspring can feast on during the long summer. Sandhill cranes, like their relatives, are iconic birds that stand 3 to 4 feet tall on their spindly Ichabod crane legs. These birds are so charismatic that they attract over 50,000 birdwatchers to the U.S. from almost 50 foreign countries, generating $11 million for local economies every year. With climate change, cranes around the world are experiencing more flexibility in breeding season length, and sandhills may become resident around the Platte River area. Whenever you can see these majestic birds in flight in North America, it's a special sight. Flight, of course, is the main mode of locomotion for sandhill cranes, as it is for most birds. Birds use their powers of flight for migrating, avoiding predators, and even for feeding. Of course, wing shape is different based on the needs of the birds. We are familiar with the amazing speed of peregrine falcons, the fastest birds, which have aerial dives clocked at over 175 miles per hour. A peregrine falcon's speed-designed wing has a fighter jet's triangular wing shape, and the falcon can morph those wings as its dive accelerates into a tight vertical tuck. At top speed, the wings are held tightly against the torpedo-shaped body. Compare these to the slow flight wings of owls that are large, broad, and rounded for stealthy flight through forests. Owls' wings can also be slightly morphed to optimize wing shape at different speeds, and they are quiet due to fringed feathers around the wing margins. Each of these is drastically different from the non-flying wings of kiwis, rheas, and other flightless birds, which might be vestigial, used for balance when running, or in the case of penguins, for swimming. But no matter what type of wing a bird has, The basic physics of bird flight are the same as the physical rules that allow modern aircraft to fly. Lift is produced by the action of airflow on a bird's wing, which is curved like the airfoil-shaped wing of a jet. Drag is caused by a combination of the bird's weight, which tends to push the bird groundward, a frictional drag caused by friction on all body surfaces, a form of drag produced by the front end shape of the bird, and a lift-induced drag. These drag effects are reduced by streamlining the shape of the bird's body and wings. Bird flight also requires specialized bone structure. Bird bones are hollow, with stiffening struts and air spaces that replace bone marrow found in other creatures. These pneumatic bones are particularly strong and light. Bird flight muscles are arranged on the breast and anchored on the breastbone or keel to keep the center of gravity low on the bird's body. Contraction of the bird's pectoralis muscle pulls the wing downward, while relaxation of that muscle allows the wing to be pulled upward as the supracoracoideus muscle contracts. All of this takes a lot of energy, of course, and birds need to have good nutrition to be able to fly. Researchers at Stanford University have discovered that long-standing models of the physics of flight are based on a very limited set of measurements. Before their experiments, measurements of the movement of air behind a flying bird were taken just a few wing beats behind a flying animal. As a result, it was generally accepted that these air currents, known as vortices, were like the puffy clouds that form and then slowly dissolve in an airplane's wake. The researchers at Stanford developed new methods of measurement using harmless lasers and a cloud of non-toxic particles, which allowed them to measure a bird's wing vortices across a bird's entire flight path. This technique revealed that the vortices actually dissolve violently and suddenly within 2 to 3 beats of the wing. This research upended the way both zoologists and aeronautical engineers thought about flight, and may have important implications for the design of tomorrow's helicopters, jets, and drones. You can't talk about the phenomenon of flight without talking about migration. So let's talk to conservation scientist and head of Smithsonian Conservation Biology Institute's Migratory Bird Center, Dr. Pete Mara, about his studies of the biology of bird migration to get more details about one of the most interesting events in the animal kingdom, migration by flight. Tell me something about the energetics and nutritional needs of migratory birds, and especially the shorebirds that you study out here on the Chesapeake Bay.
Yeah, it's such an interesting question because these birds, shorebirds in particular, but all these migratory birds go over such large distances, and many of them, not all of them, migrate at night. Some of them migrate during the day. But that takes a lot of energy. That's like, if you're driving across the US, you've got to make a lot of stops at the gas station to fill up your car with gasoline. Well, these birds don't have the luxury of stopping at a gas station. They've got to eat. They've got to eat all the time in order to build up their fat loads. They've got this muscle mass on their chest, which allows them to make those really amazing flights. But they got to have that fuel, and that fat that they build up around their bodies during migration is that fat that they use. It's that gasoline. And right over here in the Delaware Bay, there's this amazing thing that happens every spring, this synchrony of horseshoe crab spawning that occurs, and where these horseshoe crabs all come to the Delaware Bay, and they shed millions and billions of eggs, these little, basically, these fat globules that these shorebirds stop and take advantage of and just eat and eat and eat. And this is their last stop before they jump up to the Arctic to breed. And so this big infusion of fat, these horseshoe crab eggs, provides that important fuel, so these birds will have the energy to make that next migration back up to the Arctic.
And how long is the next leg?
The next leg could take a week, could take 10 days. These are the sorts of things we're just starting to learn as we track these birds. But they'll make quick stops, but they won't have the same sort of stops that they have here in the Delaware Bay and be able to refuel that much. Could take a few birds 3 days. It depends on how much fattening they're able to do before they head north.
What do we know about the navigational aids that birds use to go from point A to point B?
It's a really good question. These birds use a variety of things to navigate back and forth between their breeding grounds, where many of them go to every year, back to the same exact territory, down to the non-breeding grounds, sometimes all the way down to Argentina, to the same beach, and we know they go there every year. And they use a variety of things at a variety of scales. So they'll use everything from the stars to landforms and mountains and fields and coastlines to navigate, much like we do when we walk around town and we use landmarks to get where we need to go. But they also have a memory, so they can keep track of this information, so they'll remember it year after year.
Is that true even for little birds like hummingbirds or other little birds that only last 2 or 3 years maybe?
Yeah, it is. It is. And some of those birds will last even longer than that, 5 years, 6 years. It's really advantageous for them to get back to that same breeding area, breeding territory, where they were successful the year before. It's too risky to go someplace entirely new. So over time, evolution and natural selection has allowed these animals to build these memory banks or these different cues that they use to be able to find their way back and forth between their breeding grounds and their non-breeding grounds, and also the routes they take on migration.
What are the biggest threats to migratory birds?
Yeah, and so, before I describe the threats, I should tell you that over 40% of the birds in North America, most of which are migratory, are declining significantly. So we're in a real crisis here, trying to understand why these birds are declining and then trying to remove those threats. These threats vary. I mean, the biggest threat, of course, is habitat destruction, both here in North America on the breeding grounds and also in the tropics. That's easily the biggest threat. One of the biggest threats in the future is climate change, and we don't really know how that's going to impact birds, but we're certain it's going to take some bird species out over the next 50 to 100 years. But there are other threats as well. Buildings are a problem, wind turbines can be a problem. There are a variety of other smaller things that probably take out a good number of birds as well.
Is there something that people at home or at work can do to help conserve migratory birds?
There's actually a lot that people can do at home. I really love the old saying that, act locally, think globally, because that's really, really true. People can plant native plants. Native plants it's not just about, stopping invasives. Native plants have all of these really cool insects that have evolved with their tissues that provide food for birds. And so we've changed the landscape of North America by introducing all these non-native plants into people's yards. We've got to replant, reforest, rehabitat, restore these urban areas or where people live into these more native landscapes. It's really important. And also doing things like putting out water, really important for birds. Simple things like that can really make your own yard a wonderful bird habitat.
I'm guessing if insects are so important for migratory birds, reducing the use of pesticides at home and at work is also important.
Yeah, another no-brainer, really important thing to do. And the thing about pesticides is it's not just good for the birds, it's good for us, right? The last thing we want to do, because we all live in an area that eventually is downstream of somewhere else. We don't want to use pesticides. It's not good for our own health. Most of these things are carcinogenic at some level, and we don't want our children or our children's children to live in an environment that's contaminated. It's the last thing we want to do. So it's good for us and it's good for the birds.
Can you talk about Smithsonian's commitment to studying migratory birds, how many bird species you're looking at, and your overall program?
Sure. So back in 1990 or so, my predecessor here at the Migratory Bird Center, Russ Greenberg, published a paper, a very famous paper, that was one of the first papers to point out that we're losing a lot of our species. And Congress noticed this and said, we need to establish a center, the Migratory Bird Center. We're just dedicated entirely to the study and the appreciation and the education to people out, the public, about migratory birds. We study anywhere from 50 to 75 different species, mainly songbirds, but we're also doing shorebirds, we're doing seabirds, we're doing gulls. We're expanding in the high Arctic, because the Arctic is this place, because of climate change, that's changing really rapidly. So we track these birds throughout the year. We study them throughout their full annual cycle, which is one of the things that makes us really different, because we understand that what happens to these birds in the wintering grounds in the tropics really influences things that happen on breeding areas as well. So we have a really sort of a full, inclusive study of these birds, and we do it over the long term. So the answers we get are pretty important and often right on.
Studies of migration are kind of a subset of animal behavior. How do your studies kind of inform theoretical animal behavior in general?
We pride ourselves in the fact that a lot of our research is fundamental, but doing conservation biology is ultimately founded on these foundations of fundamental ecology and behavior. We all like to watch birds. That is behavior. Every time you see a bird do a different behavior, that's bird watching. That's what we do. So we try to study how animals move. That's behavior. That influences understanding why they die or where they go. It's all fundamental to understanding the population size, whether they're increasing or they're decreasing over time. And so we apply that information, that fundamental behavior about movement, to population size and then conservation.
We've got a lot of birds singing around us right now. For someone who's not familiar with birds and bird conservation, they might think, oh, I'm hearing a robin, I'm hearing a catbird, everything's fine. Can you elaborate a little bit more on how birds are in trouble, and especially migratory birds?
Sure. So yeah, we're hearing a mockingbird. There was a catbird singing a second ago. There was even a nuthatch. And DC, if you don't know, is actually quite the forested city. And so you get a lot of really cool birds and interesting birds right here in the nation's capital. That being said, these are fairly common species. These are also fairly generalist species, so they can adapt to a variety of situations. It's the 40% of the other species that are out there that might be a little bit more specialized, that might need a particular type of habitat, that might require a particular type of food. Or the red knots, the long-distance migratory red knots in the Delaware Bay that require, and over thousands of years, have synchronized their migration to these specific stopover areas that are timed to refuel with horseshoe crab eggs. Once we start tinkering with these systems, these really specialized systems, once we start taking out habitat, putting in new predators, these are the problems. These are the species that get affected first, these ones that are more specialized. And that's why we're seeing these massive declines that are only going to get worse as our climate continues to change and we start to really see some of the impacts from long-term climate change.
You've been studying migratory birds now for a pretty long time. What's been your biggest surprise in these studies?
You know, one of the biggest surprises for me has been that people haven't really taken a full annual cycle approach to our science and to our conservation. They've been focused just on studying the short breeding season period. And what we've shown in our research is actually that the number of young that birds fledge on their breeding grounds is actually driven by things that happen to them in the tropics, in places like Jamaica and Belize and Guatemala and Peru and Chile. And so unless we start to, actually break down our borders more and more when it comes to conservation, we're going to lose so many of these species because their life cycles don't necessarily conform to the geographic boundaries that we've set up. So we've got to come up with some new tools, some new partnerships if we really hope to do effective conservation in the long term for species like migratory birds, the ultimate ambassadors.
There's a large colony of black-crowned night herons here at Smithsonian's National Zoo. Can you talk about them?
Yeah, it's really kind of funny. It's a colony that's been here for over 100 years. The zoo's been here for over 100 years too, of course. But this colony's been nesting there for over 100 years. They arrive in March, they're here till August, and then they've disappeared. And no one's really known where they go. But it's a wonderful example of where you've got this wild population right above the actual birdhouse, nesting right above there. And so a few years ago, we started attaching satellite transmitters to their backs to figure out where our black-crowned night herons from the National Zoo were going the rest of the year, and we found that they've been going all over the place. Some actually stay right here in Georgetown, whereas a few others go all the way down to Florida, down to almost to the Everglades. So enormous variation in where these birds are going. So it's pretty neat.
Can you talk about the Olympians of the bird world?
Yeah, so the Arctic tern is probably the one most people think about. It's a water bird species that migrates basically from the South Pole all the way up to the North Pole, migrating anywhere from 10 to 15,000 miles a year, twice a year, up and back, which is a pretty tremendous feat. The black-polled warbler is a small warbler. It weighs about as much as a quarter. This bird triples its body weight. I mean, triples its body weight. And it goes up to the breeding grounds in the boreal forest. It goes off of Newfoundland, this population, these species, and goes down the Atlantic almost for 2 or 3 days on the wing, on the wing, a small warbler weighs about as much as a quarter, just depending upon its fat loads, and then hits the Caribbean or South America, and then spends the rest of the winter in Amazonia. But that's an amazing, amazing migration for that size bird. And then there's penguins, of course, that do deep diving in the Antarctic that also puts them into these really interesting environments that you wouldn't normally think an animal that spends most of its time in a terrestrial situation or at the surface of the water could actually withstand, but they do.
I've been focusing on the use of wings for flight, but as Pete just pointed out, wings are about more than flying. Some birds, including penguins, evolved from flying ancestors, but have lost the ability to fly because of different pressures in their ecological niche. For example, penguins' water-adapted wings let these flightless birds swim through the water at great speeds while they're fishing or avoiding predators. That's a much greater survival advantage for a large bird in the Antarctic environment than the advantage of flight that we observe in other birds. And penguins aren't the only birds to abandon the skies. What about the famously flightless big birds, the ratites? This group includes extinct species like the moa and living species like the ostrich, along with a number of others. Although the chicken-sized South American tinamous are flighted members of this flightless bird group, all other birds in the ratite group do not fly. According to DNA analysis that examined the relationship between tinamous, rheas, ostriches, emus, and kiwis, tinamous are one of the most ancient members of the ratite group. The relationship analysis suggests that the common ancestor of ostrich, rhea, and emus was like the tinamu, and that each of the unflighted species lost its ability to fly independently and on several different occasions. Rheas and ostriches kept their wings and developed fluffy feathers and used their wings as rudders when running fast on the grasslands, where they are adapted to live with hoofed mammals and other grass eaters. Emus and cassowaries have reduced wings, suitable for large birds that live in forests. The wings of New Zealand's kiwis are incredibly vestigial. Their feathers are the most hair-like of all the ratite's feathers. And these nocturnal birds that live in burrows are the most mammal-like of all birds. These amazing non-flighted birds evolved to occupy special niches that were vacant of mammals while all other birds were evolving to aerial niches. Birds began their evolution millions of years ago and have conquered the air, many watery habitats around the world, and all terrestrial habitats. They are magnificent flying animals, and we are constantly learning more about their flight anatomy, physiology, and biology. Some of our increased understanding can help humans create a better world for ourselves. For instance, the highly evolved shape of a kingfisher diving cleanly into the water at high speed has helped a birdwatching engineer to increase the efficiency of a bullet train entering a tunnel. And some of our increases in knowledge can help us make a more sustainable world for birds, as Dr. Mara's research suggests. If you want to participate in migratory bird conservation, here's what I recommend. Learn more about your local gardens to increase your use of native plants and reduce or eliminate any pesticide use. And maybe you can practice some mindfulness by slowing down and just watching the birds in your backyard, local park, or zoo. You will be amazed at the behavior and flight abilities of your backyard birds.